Now on the next page, what you see is the unit circle, which is something that you've all seen at some point in high school. Now it is worth knowing these values, these trig values all around this circle, because they do come up quite often throughout the course. So ideally, if I ask you, for example, what is sine pi over 6, then you would be able to answer right away that it is a half, and so on. So take your time to memorize these values if you haven't already. And remember that you just have to know the values in the first quadrant, and then all these other values you can get by symmetry. I won't go into any more detail than that. And there are some worksheets in Moodle that you can try as extra practice. Now moving on, we're going to look at inverse trigonometric functions for sine, cosine, and tangent. So the first one we will look at is the sine inverse function, also known as arcsine. We're going to start off with the graph of sine x, which is given here. You should definitely know how to draw this from memory as well. Now I want to find the inverse of this function, but if you notice, this function here is not one-to-one. If I draw a horizontal line here, for example, the graph crosses this horizontal line many times, in fact infinitely many times, because this graph does go on forever in both directions. So it is not one-to-one. So what do we even mean by inverse if it's not even one-to-one? Well, here's what we're going to do. We're going to restrict the domain of this function. Right now, the domain is all real values from minus infinity to positive infinity. We will restrict our domain to be from minus pi over 2 to pi over 2. So when we're looking just inside here, you will notice that it is one-to-one. If I draw a horizontal line wherever within this domain, no matter where I draw this, my horizontal line will cross the curve at most once. So that's what we're going to do. We're going to restrict our domain to be from minus pi over 2 to pi over 2. And because I'm including the endpoints minus pi over 2 and pi over 2, I have these square brackets. So now we have a one-to-one function, and we're going to find the inverse function just within that domain. So let's first look at what the graph of the inverse sine function looks like. Now the inverse sine function can be written like this, with the -1 as a superscript, or as arcsine x. I will be using them interchangeably. So as we discussed earlier, we know how to draw the graph of the inverse given the graph of the original function. This dotted curve is the sine function within the domain minus pi over 2 to pi over 2. Now to draw the inverse, remember what you do is you reflect the curve around the line y is equal to x, which is that line there. And I've already done that for you. This red curve is what you will see in the reflection. So that is the graph of your sine inverse function. So let's look at the domain and the range of this inverse function. Remember that when you're taking the inverse, the domain and the range flips around. So we know that the domain of our sine function was restricted to be from minus pi over 2 to pi over 2. So that is going to be the range of the inverse function. So the range is from minus pi over 2 to pi over 2. Again, square brackets because we're including those endpoints. And you can verify that that is the case by looking at the graph of sine inverse up here. The y value does go from minus pi over 2 to pi over 2. Now, the domain of arcsine is the range of sine. Well, if you look back to the sine graph here, the range is from -1 to 1. So that is the domain of your inverse, including -1 and 1, so square brackets on both sides. And again, you can verify that that is the case by looking at the graph here. The domain is the x values, and it does go from -1 to 1. Now, keeping this range in mind, we can now solve something like this. arcsine of a half. Now what I suggest you do first here is set this equal to theta, because we know that the answer will be some angle. Remember, for arcsine, the input is going to be some number between -1 and 1, and the output is going to be some angle between -pi/2 and pi/2. Now that you have this equation, you're going to rewrite this without the inverse. So equivalently, we can rewrite this above equation as sine theta is a half. Remember, you can get rid of the inverse sign by flipping the input and the output. That's what I've done here. Now, as it is here, there are infinitely many angles that satisfies this equation. Let's take a look at the graph of sine theta above. Half is, let's say, here. Then there are infinitely many points where the sine function is equal to a half. However, for questions like these, there is only one answer. And to figure out that one answer is by remembering that your angle is always going to be between -pi/2 and pi/2. So that means, well, remember -pi/2 is here, pi/2 is here, so your answer is going to lie somewhere on that part of the circle. Well, if sine is positive, that means the y value is positive, so you are going to be up here. So at some point here, the y value is a half. All right, so let's fill this out first. Remember that your angle is always going to be between -pi/2 and pi/2, so we'll fill that out here. And hopefully you all know what this angle is. The point on the first quadrant where the y value is a half is 30 degrees, or in radians, it is pi/6. In this course, we'll be using radians for the most part, and you should be able to answer these kinds of questions in radians, not degrees. All right, so very similar thing happens for the inverses of cosine and tangent. So for the cosine graph, which you can see here, again, it's not 1-to-1, so we make a restriction on the domain of this function to be between 0 and pi. So when you're here, your graph is 1-to-1, and then it can have an inverse. So I have that restriction written down there. And when you take this graph and reflect it around the line y is equal to x, you're going to get this. And that is your cosine inverse function graph. And lastly, for y is equal to tan x, which has a graph like this, again, it's not 1-to-1, so we make a restriction. We only take the x values going from -pi/2 to pi/2. And again, when we do that, we do have a 1-to-1 function in there. So there's your restriction. Notice that we do not include -pi/2 or pi/2 because the graph never goes through those points. They're vertical asymptotes. And when you reflect this curve around the line y is equal to x, you're going to get this kind of a shape. So this is your graph of tan inverse x, also known as arctan x. All right, so at this point, it would be good for you to pause this video to work on these two examples. It's very similar to what you did in this example, but now we're looking at arc cosine and arctangent. For this arc cosine of -1/2, we start off the same as before, so we set this equal to, let's say, theta, and then we'll rewrite this equation without the arc cosine, so just in terms of cosine, and that would be cosine theta is -1/2. Again, we're flipping the input and the output around when you get rid of the inverse. Now, just like before, there are infinitely many answers to this equation, but when we have the restriction, you'll find out that there is only one answer. So the restriction, if you remember, is from 0 to pi. So let's write down here the restriction. And that means on the unit circle, we are only looking at the interval from here to here, right? 0 is this angle there, and pi is 180 degrees, or this angle here. So it turns out that within this highlighted region, there is only one answer. Now remembering that cosine is the x value is negative only here. So you're somewhere along there. And at some point, apparently you're going to have an x value of -1/2. So we want to know where that is. Well, that's 2 pi over 3. So we have our answer. Theta is 2 pi over 3. Similarly, for this other example, arctan of 1, we're going to set it equal to theta, rewrite this without the inverse, so that means tan theta is 1. And remember, our restriction for tangent was from -pi/2 to pi/2. So let's write that down here. And that corresponds to this part of the circle. And tangent is positive only in the first quadrant, so you're somewhere along there. And if tangent is 1, that means sine over cosine is 1. Let me write that down, because tangent is sine over cosine, right? Now, if you cross multiply, you get sine theta is cosine theta. So we need to figure out where in this part of the unit circle sine is equal to cosine. In other words, x is equal to y. Well, that happens at the 45-degree angle, or pi over 4. If you remember, the coordinates at that point is 1 over root 2 and 1 over root 2. So we found our angle. It's pi over 4. All right, let's try some composition questions. So we're going to be composing a trig function with some inverse trig function, and we're going to try to simplify this as much as possible. Here's how you should start. Let the inside function, in this case arctan x, be some letter like y. So I've already written that down here. And then write this equation without the inverse sign. So that means tan y is x. And remember that when we're looking at the inverse, that automatically means that there was a restriction on the angle y. And if you remember, the restriction is from -pi/2 to pi/2. These are open brackets on both sides. Okay, now we're going to utilize a right triangle. Tangent denotes opposite over adjacent on a right triangle. Right, so if y is the angle here, tangent is this length divided by this length. So if tan y is x, we can think of x as x over 1. So we can think of this length as x and this length as 1. And our goal is to figure out cosine of y. Let's actually write that here. If y is arctan x, that means it's the same as cosine y. Here's y. So on the right triangle, cosine is adjacent over hypotenuse. So here's the adjacent, here's the hypotenuse. So if we just know what this length is, then we can figure out cosine y. Well, that's easy to do by using the Pythagorean theorem. Let's call this z and figure out what z is by using the Pythagorean theorem, which says 1 squared plus x squared is z squared. So z is plus or minus root 1 plus x squared. But remember that because we have this restriction, you have a unit circle and you're only looking at the angles from here to here. And you should notice that cosine is always positive in that region. So that means since cosine is 1 over z and 1 is positive, z must also be positive. So let's write something like, since cosine has to be positive or 0, so greater than or equal to 0, we choose z is also positive. Z is root of 1 plus x squared. And so finally, cosine y is, again, adjacent over hypotenuse, 1 over z, which is 1 over root 1 plus x squared. And that is the same as cosine of arctan x. Now, it would be a good idea for you to pause the video here and work on this one yourself. It's very similar to what you just did above. So the first thing you do is you set the inside function to be some letter like y. So let's write that down. Y is arcsine x. And then rewrite this without the inverse sign. That would mean sine y is x. And remember the restriction on the y. It's between minus pi over 2 and pi over 2. All right, now using this equation, we're going to build our right triangle here. So let's say y is this angle. Remember, sine is opposite over hypotenuse. So since sine y is x, or x over 1, we can think of the opposite side as x and the hypotenuse side as 1. And our goal is to figure out cosine of y. So that's adjacent over hypotenuse. So that means we have to figure out this length. Again, let's call this z and use the Pythagorean theorem to figure out z. The Pythagorean theorem says z squared plus x squared is 1 squared. So z squared is 1 minus x squared. So z is plus or minus root 1 minus x squared. Now only one of these signs is correct, so just like before, let's draw our unit circle to figure out which one it is. If y is between minus pi over 2 and pi over 2, then we're looking at these two quadrants, so you're somewhere along there for the y value. And cosine is always positive there again. So that means we're going to take the positive sign. So cos y is bigger than or equal to 0 in the interval from minus pi over 2 to pi over 2. So since cosine is z over 1, to make z over 1 positive, we have to take z equals to positive root 1 minus x squared. So cosine y is z over 1, or simply root 1 minus x squared. All right, so that's the end of the review. Lots and lots of homework questions assigned for you from 1.5 of the textbook. Please do them all, and then once you're done, we will move on to calculus.